In this video, I'm going to discuss about the applications of mesomeric effect under the subtopic mesomeric effect. I've already discussed about what is mesomeric effect in my previous video. Let's see its applications now. The mesomeric effect is used to explain the acidity of phenols, acidity of carboxylic acids, basicity of enolines, acid stability of carbocations and stability of carbanions. Before going to the acidity of phenols here, let's understand what are phenols here. Phenols are nothing but the hydroxy benzene is nothing but a hydroxybenzene where the OH group is attached to the benzene ring here. Yes, let's now look at the acidity of phenols. What are acids? The acids are nothing but the proton donors. We have already read about this. The substances which are able to donate the protons are nothing but acids here, and the phenols here can donate the protons here. So it's an acidic in nature. And this acidity can be explained based on the stability of the phenoxide ion and the phenols here. So it can donate the proton resulting in the formation of phenoxide ion and the hydronium ion here. And these phenols are acidic. Why? Because the phenoxide ion is more stable than phenol because of, and this can be explained based on the mesomeric effect. And so the equilibrium will shift towards the right side, shift towards the phenoxide ion side because the phenoxide ion is more stable than phenol here. And the stability can be explained based on the mesomeric effect or the resonance. If you look at the resonance structures of phenol here, yes, resonance structures of phenol here, there are 5 resonance structures which are possible or the canonical forms, and the OH is electron releasing group, that is plus M group. It will release the electrons into the system, and 5 resonance structures are possible for phenol, and this is the resonance hybrid here, which is shown here. And as you can see that there is a charge separation which is present here. There's a partial negative charge we can see on the ring and the partial positive charge on the OH here, So there's a charge separation because negative charge in the part of the molecule and the positive charge in the other part of the molecule. So there's a charge separation here. And when we look at the phenoxide ion here, when we look at the resonance structures of the phenoxide ion here, again, there are 5 resonance structures which are possible here. This is donating the electron density into the ring. And when we look at the resonance hybrid of this phenoxide ion here, there is a charge distribution or the charge delocalization which can be seen in the phenoxide ion. The whole molecule is sharing the negative charge here. There is no charge separation, and because of this very same reason, the phenoxide ion is more stable than phenols phenol. Yeah, when we look at the resonance structure, I mean the resonance hybrids of these both the structures here, there's a charge separation which is seen here, and there's a charge delocalization or just charge distribution in the phenoxide ion, and because of this reason phenoxide ion is more stable, and so the equilibrium is shifting towards the right side, resulting in the proton donation. And if it's a proton donor here, we can see that if it is donate a proton here, then it acts as an acid. So phenols acts as weak acids. Yes, and the acidity of carboxylic acids can also be explained based on the mesomeric effect here, and this is an acid RCOOH. Uh, and we have just now seen that if it's a proton donor, it's an acid, it can donate the protons here, resulting in the formation of carboxylate ion and hydronium ion here. And again here, this the acidity of carboxylic acids can be explained based on the mesomeric effect because the carboxylate ion is more stable than carboxylic acids. And this can be explained based on the resonance effect. Let's see the resonance structures of both this carboxylic acid and the carboxylate anion here. And this is the acid here and carboxylic acid, and this is an anion here. When we look at the resonance structures of both these, there are two resonance structures which are possible for carboxylic acids, and there is charge separation we can see here. See, there's a positive charge and here is a negative charge. So there's a charge separation again see here, and there is a charge delocalization. The negative charge is shared by both these oxygen atoms here. Uh, so there's a charge distribution or delocalization in the anion. And one more thing we can, if we closely observe the structures, you can see that there are equivalent resonance structures which are possible for carboxylate anion here. The structures are equivalent when we look at the position of the nuclei here, C, O, and R, we can see that they are equivalent. The oxygen atom is showing the negative charge here and here it's sharing here. So they are equivalent resonance structures, two equivalent resonance structures possible here. And there are two non-equivalent resonance structure which are possible here. This is because if you look at the resonance structures here, they're not equivalent. There's plus and minus charges here. There is no such charges seen in the first structure. So for these two reasons here, carboxylate ion is more stable than carboxylic acids. So it acts as an acid here. Yes, they can donate the protons and it can act as an acid here. Yes. See, if you look at the resonance hybrids of both these, charge separation here and there's a charge distribution here, and there are equivalent resonance structures which are possible here, and there is non-equivalent resonance structures which are possible here. As such, this a carboxylate anion is more stable than carboxylic acid, so the equilibrium is shifting towards the right side, so it can donate the protons easily. It can donate the protons easily. The acid can donate the protons easily, so the carboxylate ion is formed easily here. So carboxylic acid is a acid as an acid. So we can as well compare the acidity of phenols and carboxylic acids based on the mesomeric effect here. See, when we look at the resonance structures of these two, there is a we can see that there are only one oxygen atom which is carrying the negative charge here, and there are two oxygen atoms here, only one oxygen atom, and there are two oxygen atoms which are sharing the negative charge here. So we know that the more electronegative atom sharing the negative charge is more stable. In both the cases, the oxygen atom is carrying the negative charge, but here there are two oxygen atoms, here only one oxygen atom. So for this reason, the phenoxide ion is less stable than carboxylate ion. And one more reason is when we look at the resonance structures for the phenoxide ion, here there are 5 resonance structures which are possible, but all these are non-equivalent. When we look at the structures here, so there's non-equivalent here. These two oxygen is not having the charge, and these three having the charge here. So these are all non-equivalent here. But when we look at the carboxylate anion here, there are 2 resonance structures and which are equivalent resonance structures. So there are 5 resonance structures which are possible for this are 5, and here 2 equivalent, here 5 non-equivalent. Even though the number of the resonance structures are more here when compared to that of the carboxylate anion here, since these are equivalent for carboxylate anion, this is more stable when compared to that of the phenoxide ion. So the equivalent resonance structures, I mean the the molecule having the equivalent resonance structures is more stable than that which is having the non-equivalent resonance structures. Even though it has 5, it is less stable because their resonance structures which are possible for carboxylate anion is equivalent here. So because of the 2 oxygen atoms carrying the negative charge and 2 equivalent resonance structures possible for carboxylate anion is more stable than phenoxide ion. So carboxylic acids are stronger acids than phenols. Carboxylic acids are more acidic than phenols because a carboxylate ion is more stable than phenoxide ion. Now let's see the effect of inductive effect and mesomeric effect on the acidity of phenols and carboxylic acids here. Yes, if you see that the plus M and plus I groups will decrease the acidity. Why this? Because this and minus M and minus I groups increase the acidity. Yes, when we look at the, for example, the nitro group here, it is an electron withdrawing group, that is minus M effect group. Yes, this is a minus M effect group. It will decrease the electron density on the ring. It will decrease. So, if it decreases electron density on the ring, it's decreasing the electron density on the oxygen, OH oxygen, which is donating the proton. So OH bond dissociation becomes easy here. It can easily give away the proton here. So it is more acidic when electron withdrawing group or the minus M effect groups are present on the ring. It will make the OH bond dissociation easy because it will decrease electron density on the oxygen. So it can easily donate the protons. If it can easily donate the protons, it can act as an acid. So what are acids? They are proton donors. If it able to donate the protons easily, it acts as an acid. So minus M and minus I groups increase the acidity. So orthonitrophenol is more acidic when compared to the phenol because the nitro group, which is electron withdrawing group or minus M effect group, is present on, this is minus M effect group is present on phenol. So it is increasing the acidity of phenols. On the other hand, if plus M or plus I groups are present, for example, the plus I, which is CH3, for example, it will donate the electrons into the ring, onto the CH, onto the benzene ring, for example, onto the benzene ring. It will donate the electrons into the ring. Yeah, when there is plus I group like CH3 group here, it's a plus I group. It will increase the electron density on the ring. Yeah, if it is, it will increase the electron density on the ring as such. So it will increase the electron density on the oxygen also. So it will decrease the bond dissociation of OH. The bond dissociation of OH becomes difficult, so it cannot donate the uh, uh, proton easily. So as such, it will decrease the acidity. So plus M and minus I groups, plus M and plus I groups decrease the acidity, and minus M and minus groups increase the acidity. It can be explained based on these following examples here. Yeah. Now, based on this mesomeric and inductive effect, let's put these in an order of their decreasing order of their acidities. Let's put these compounds in the decreasing order of their acidities. If you look at the acidity of phenols, orthocresol, orthonitrophenol, and orthochlorophenol. Yes, and yes, this methyl group, we know that it is an plus I group, and nitro group is an minus M group, and this one is minus I group. So we know that this minus M group will increase the acidity because they will decrease the electron density on the oxygen, and the OH bond dissociation becomes easy, so the proton can be donated easily. So orthonitrophenol is more acidic when compared to that of other phenols here. Now let's look at the acidity of orthochlorophenol here. Now this is minus I effect. So this will also withdraw the electron density from the ring. making the bond dissociation of OH easy, but the inductive effect is less than mesomeric effect, or the mesomeric effect predominates over the inductive effect. So this is more acidic when compared to that of chlorophenol. So orthonitrophenol is more acidic than orthochlorophenol. Then comes phenol here because H has no effect here. And when we look at this CH3 or CH3 at the ortho position here, orthocresol, there's a plus I effect here. So it will release the electron density into the ring, making the OH bond dissociation difficult because it will electron density on the oxygen is increased. It cannot dissociate easily. It cannot donate the proton easily. So this is less acidic. So this is the order of the acidity of the phenols based on inductive and mesomeric effect. Yes. Now, when we look at the acidity of a few of these carboxylic acids here, this is the first one is, yes, acetic acid, chloroacetic acid, formic acid, and this nitro-substituted acetic acid here. Again, the same order follows. This nitro is minus M group. It will withdraw the electron density from the ring, so thus increasing the acidity of the acid here. So this one, nitro substituted acetic acid, is more acidic than chloroacetic acid, and this chloro group is minus I group here. And as mesomeric effect predominates over inductive effect, chloroacetic acid is less acidic. And then comes the formic acid because H has no effect here. And then comes acetic acid 3CH3 is an plus I effect group. It will increase the electron density in the system, making the bond dissociation difficult. This is the order which is followed in the acidity of carboxylic acid based on the inductive and mesomeric effects. Yes.